All right, kids, ready for some more partial derivatives? I thought we'd do a little more practice with this first one before we go on, or with the objective from yesterday, before we continue with it today. So, modeling how to, read this, Remember, you are reading this one this way. So it says find the partial with respect to x first. So everybody here is a constant, right? So you think of this as ln of x plus 2 plus 3, or ln of x plus 5 if you want, right? What is the derivative of ln x? Well, isn't it 1 over the stuff times the derivative of the stuff? But remember, the derivative of this inside stuff with respect to x is the derivative of x, which is just 1, times the derivative of a constant, 0, plus the derivative of a constant, 0, plus the derivative of a constant, 0. That's it, right? So now, what is the derivative of that with respect to y? So the derivative of what I just did with respect to y is this stuff, right? That's really x plus 2y squared plus 3z squared to the negative 1. Do the chain rule, that's negative 1 to all that stuff to the negative 2 times the derivative of that inside. But the derivative of the inside with respect to y only. Everybody else is a constant, right? So the derivative of x is going to be 0. The derivative of 3z squared is going to be 0. And you just have 4y, right? Check. Now I have to take the derivative of that with respect to z. So what is that? Well, with respect to z, here's the only thing that has a z in it, right? So this is really just negative 4y times all that stuff to the negative 2. Now remember, there's a z thing in here, though. I have to worry about. Bring down the negative 2. Copy over the stuff to the negative what? Times the derivative of the middle. But the derivative of the middle with respect to z is only the derivative of this term, right? There's no z's in those. So that's just times 9. Oops, I think I wrote, this is a cubed way back here, isn't it? Cubed, cubed, cubed. That's where I got my 9 from. 9z squared. So clean that up a little bit. And if you really wanted to put that in a denominator, cubed, that's also fine. Okay? So looks devastating is really not if you kind of take your time. Do it in the right order. All right, so remember what we were doing with the second derivative in Calc 1, right? No soup for you. Do you remember that concavity? Where I talked about the first part of that graph, right, being concave down, and the second part being concave up, and where you change concavity is called the point of inflection, right? So this whole part of the graph is concave down. This whole part of the graph is concave up. I call that soup for you, right? That's like a soup spoon. This is concave down. I call that no soup for you because you can't get any soup if you use your soup spoon that way. And then again, where the second derivative is equal to 0 is where you change concavity. Well, think about again what that means as far as rates of change. Do you remember? Right? The first derivative is the tangents. What are the tangent lines doing? Here's the tangent lines 0, tangent lines negative, tangent line still negative, tangent line 0, tangent lines positive. The second derivative tells you the rate of change of the rate of change, right? The slopes of the slopes. You remember that? It's the rate of change. In other words, what are your tangent lines doing? Your tangent lines are positive, but your tangent lines are decreasing to 0. Your tangent lines are negative and still decreasing, right? Still decreasing. Then your tangent lines are still negative, but they are now starting to increase, right? The rate of change is increasing. The rate of change is 0. The rate of change is now positive, and the rate of change is increasing. What is the rate of the rate of change? That's your second derivative. Right? Remember, when your second derivative is positive, when your second derivative is negative, and you change concavity when your second derivative is equal to 0 or does not exist. So, what about partials? Look at that, right? What the heck? Question mark. What is happening? Well, look at that cool looking graph. What about, can you see soup for yous and no soup for yous all over the place in this crazy three-dimensional swoopy splitey thing? So what the heck? And actually, in multivariable, not only are we interested in finding second derivatives, but where the sum of the partials are equal to 0, that's something that we call steady state. So why do we care about when the second derivative, right, the second derivative of some function u with respect to x, second derivative with respect to x, added to the second derivative with respect to y of some function, if you add them together and equal 0, that's something we're really interested in. Think about that example I gave you with temperature and relative temperature and humidity, right? And when we have two variables and holding one constant, when the rates of change of the slopes are equal, then we say we are in a steady state. When the rates of change of both variables, you add them together and you equal 0, that's called steady state. Now, depending upon where you've got, I don't know if you're in, if you're in higher level chem or higher level physics, right? Dealing with heat and water and magnetic fields, often interested in steady state. Solutions to this partial differential equation, right? When can we find, right? Can we find out where we can get a steady state? Is not where we are at yet. That's for differential equations. So all you're going to be asked for in multivariable, you will not be solving Laplace equations, and that's what these equations are called, after Laplace, another Frenchman. Oh, I forget his first name, darn it. They're called harmonic functions. They're beautiful. And if your Laplace equation, which is your second derivatives, are equal to 0, whether you're in 2 dimensions, 3 dimensions, or any dimensions, again, as far as heat, water, which is heat conduction, fluid flow, electric potential is in the magnetic fields, Laplace equations are super important. And when we're together in a live session, we'll watch some videos about these, which are really interesting, I think. Right? And again, in 3 variables, same kind of thing. Laplace, very important. That's what the 3D Laplace equation looks like, where your second derivatives with respect to each of the 3 variables is equal to 0. That's called a solution. That's called a Laplace equation, and a solution to Laplace's equation is something we'll do in differential equations, finding the solution. In this class, you'll only be asked to determine if we have a solution to Laplace's equation. So here's what I mean by that. If I give you a function u in x and y, I want you to find the second derivative with respect to x, right? So hopefully you can see that holding y constant, the derivative of a constant is 0, so the first derivative of u with respect to x is 2x, and then taking the derivative of 2x with respect to x is just 2. When I do that for y, the first derivative of u with respect to y is 0 plus 2y, and then the second derivative of that expression in terms of y is just 2. Add them together and I do not equal 0. So x squared plus y squared does not satisfy Laplace's equation. That's all you'll be asked to do in multivariable. Actually solving Laplace's equations is something we'll do again in differential equations. What this says, though, is that the rates of change of the slopes on this surface in 3D, the rates of change of slopes are not balanced. And right, I know that is hard to picture right now. But here is that picture from our first slide, right? Hopefully you can kind of see, if just looking at that picture, I hope you can see that there's some really pretty things happening, right? So if I take the derivative of u with holding x constant, holding y constant, cosine of y is a constant. So I'm just doing the derivative really of e to the negative x, which is negative e to the negative x times the constant. Again, I'm holding, who am I holding constant? I'm holding x constant. So e to the negative y is just a constant. The derivative of cosine x is just sine x times that constant. Take the derivative there. The derivative of this function with respect to x means, once again, I'm holding y constant, right? So cosine of y is just a constant. So the constant times the derivative of negative e times to the negative x. It's just here. The e to the negative y is my constant in the second term, and the derivative of a sum is just the sum of the derivatives, right? So the derivative of sine x is cosine x times this constant. Now go back to the original and hold x constant. Holding x constant, I am taking the derivative of cosine y, which is negative sine y, and then I just have this e to the negative x as a constant. Over here, cosine x is my constant, and I'm taking the derivative of e to the negative y, which is negative, which turns this negative positive, e to the negative y. And then again, cosine x is just a constant. Now take the derivative of that expression. And once again, in terms of with respect to y, so you're holding x constant again. And this is the expression I get. Now verify whether that satisfies Laplace's equation. So you want to know, here's your second derivative, right? Here's the second derivative with respect to x. Here's your second derivative with respect to y. Add them together, do they equal 0? Yes, they do, right? These terms will cancel one another out. E to the negative x cosine y added to negative e to the negative x cosine y cancels out. E to the negative y cosine x added to negative e to the negative y cosine x cancels out. The second derivatives added together equals 0. Therefore, this equation does satisfy Laplace's equation. The rates of change of the slopes are balanced. We say this function represents a steady state. All right, so again, we'll talk about in our live session. I'll kind of try to give you some visuals as to what this means, but that's the math, the mechanical computations that you're doing. All right, I will see you Tuesday.